Signal flow and data transfer are assisted within a network by various devices known as backbones. The four different backbone devices are hubs, bridges, switches, and gateways. Each device transports data in a specific way. A hub is a centralized connecting device, often located at a center of a star network, that automatically rebroadcasts any signal or data that it receives from one device to all other devices on the network. Because all the devices connected to a hub are competing for media usage, it's possible for collisions to occur when two devices send transmissions simultaneously. For this reason, it's important to avoid using a hub for messaging that requires immediate response. Another network backbone device is called a bridge. Network bridges are smart devices that process and record information about signal traffic between devices in the networks. The bridge then uses this information to determine the most efficient path for data transfer between a transmitting and a receiving device without having to send it to every device in the network. A switch is a multi-port network bridge that uses packet switching to forward data to one or multiple specific devices. Because more than one transmission can occur at a time, switch operating speeds are very fast. Switches are also full duplex devices that allow data signals to flow simultaneously in both directions. This eliminates the risk of data collisions that may occur in other network backbone devices. When two segments of the same network have different communication formats, a gateway is needed to connect them. A gateway performs a conversion function so that a computer on an Ethernet network using a TCP/IP protocol may communicate with a PLC on a subnet using the ControlNet protocol. Even though these two protocols are incompatible, the gateway can connect them on the same network and allow them to function together. Hubs, bridges, switches, and gateways, the backbones of networking, perform individual and important functions in keeping networks performing at their highest level. The purpose of an inductor is to oppose any change in the magnitude of current within a circuit. The electrical property that resists either an increase or decrease in current is known as inductance. An inductor is created when an electrical current flows in a wire wrapped around a magnetic core. You may recognize this as an electromagnet represented by flux lines that develop around the core with the formation of a north and south pole at their respective ends. To demonstrate the properties of an inductor, we'll add a resistance or light bulb to this circuit. As the switch is closed and the current flows through the circuit, the electromagnetic field in the inductor forms and expands rapidly. However, because of the unique properties of an inductor, as the flux lines of the electromagnetic field expands, the changing current generates a voltage that resists the current coming from the source. The maximum opposition to current flow occurs at the instant the switch is closed. Therefore, the bulb will not turn on instantaneously. However, once the electromagnetic field stops expanding based on the level of changing current, the flux will no longer generate an opposing voltage in the circuit. The current will continue to flow and reach its maximum value after 5 time constants, or 5t, where t is equal to L divided by R. The light bulb will then be at its maximum brightness. If you open the switch and stop the flow of current from the source, the electromagnetic field will diminish rapidly and simultaneously release stored energy in the form of voltage. It will actually generate enough voltage to cause a spark across the switch as it opens. Whereas a capacitor uses voltage to store energy, the inductor uses current. Inductance of an inductor is defined as the amount of voltage induced, divided by the change in current per second. Therefore, if 1V is induced by a change of 1A in 1 second, there is 1 Henry, 1 H, of inductance.